Welcome to today's live session. I hope people will join in between. So, this is the live session 3 uh, happening on 10th August 2024 for the course Basic Environmental Engineering and Pollution Abatement with me, Mahalakshmi S, a research scholar from NIT-Trichy. I hope the presentation is visible and the voice is audible. Can you please confirm it? You can text in the chat box also. Okay. I hope I'm audible. So this is the live session link. The same link will be used for the Saturday sessions, which is going to happen from 3 p.m. to 5 p.m. And all the live session videos are recorded and uploaded in the YouTube channel named Mahalakshmi S. You can find it through at Mahalakshmi Shekhar and NIT-Trichy. So every Saturday from 3 o'clock to 5 o'clock, I will be handling this live session for this course, Basic Environmental Engineering Pollution and Abatement. Okay. So, in this live session, first we will discuss the solutions for the assignment 1 and 2. Then we will brief about the lectures of this week, and we will also solve some sample problems for week 3. So, the first question from assignment 1 is which are the layers of the atmosphere? Find the most suitable option. Option 1 is troposphere, mesosphere, and all of these. And the right answer is all of these. So if you see the layers of atmosphere above the earth, the first layer is the troposphere, in which all the living beings are there. And there comes the stratosphere, which consists of all the ozone layer where the aircraft goes. And then the mesosphere, then the troposphere where the satellite goes, and the exosphere is the outermost layer of the earth. So here, what are the layers of the atmosphere means troposphere and mesosphere, both are the layers of Earth. So the correct answer is all of these. The second question is which of the following is a source of renewable energy? So renewable energy is which can be repeatedly used again and again without any iteration. So if you see the options, the first one is coal, next is solar energy, next is petroleum and natural gas. So coal, petroleum, natural gas, all these things once you consume it, they will be reduced. But solar energy is the renewable energy here since we can use it again and again. So which of the following is a source of renewable energy? The answer is solar energy. Next, what is the order of municipal wastewater treatment? Four options are there. The correct answer is pre-treatment, followed by the primary treatment, followed by the secondary treatment, and then the advanced treatment. If you see this, we all collect all the sewage water and it is going to the STP, sewage treatment plant. So all the sewage water are collected and it is going to the sewage treatment plant. That first step is the pre-treatment and then it is followed by the primary treatment. So firstly, there will be a bar rack and then followed by the grid chamber, then the equalization basin. Basically, what is going to happen here is all the floating materials are to be removed using the grid chamber, and then the primary settling, which is based on the sedimentation process, all the settlable items are going to settle down and the floating items are separated earlier. So this is the primary treatment. So from the bar up to primary settling, it is the primary treatment, and then there comes the biological treatment and secondary settling. So wherever the settling is happening, there will be a sludge formation. So in the primary settling, it is purely based on the sedimentation principle. Then it is followed by the biological treatment. So in the biological treatment, we can use the microbes in the wastewater itself, and we will be aerating it to ensure the degradation of the organic matter content present in the waste. So now what happens after the biological treatment is the wastewater is now going into the secondary settling tank. So here again the settling is going to happen where the sludge is formed. And then till this step it is the secondary treatment. Next is the advanced waste treatment. Here what happens is after the treated water is coming into the step, it is finally treated by ozonation or UV treatment or chlorine treatment to ensure the water is suitable for drinking or suitable for using it for other potable purposes. Next question is what is the full form of CPC? So CPCB is the Central Pollution Control Board. So why the CPCB is very important means whenever there is an impact going to happen because of the man-made activities or because of any natural calamities, all these immediate steps taken by the government or controlled mainly by this CPCB, Central Pollution Control Board. And then in the case of territories, who will be involved is SPCB. So SPCB is the State Pollution Control Board and CPCB is the Central Pollution Control Boards. Which of the following is a biotic component of ecosystem? So as we discussed earlier in the week one session, the ecosystem is composed of both the abiotic and biotic components. So abiotic components are the non-living things and the biotic components are the living things. So here in this option, air, water, soil, animals are given. Air, water and soil are non-living components of the ecosystem. Animals are the only living component of the ecosystem. So the right answer is animals. Next question is, which of the following compounds is responsible for photosynthesis? So photosynthesis is going to happen in the plants. For that, the main important component is the chlorophyll. Which of the following is or a part of risk analysis? We have discussed why risk analysis is very important and what are the components. So in this option, hazard identification and risk assessment, risk management, risk communication, all of the above are given. So in the risk analysis, all these three will be involved. The first step is to identify the hazard. Is there any hazard is going to happen? And what type of component is that? Whether it is a physical hazard or it is a chemical hazard or it is a biological hazard, we have to measure what kind of hazard is going to happen, and then there comes the risk assessment. How long that component can cause hazard to the ecosystem and the living beings. Next step is the risk management. So in the risk management, what happens after assessing the risk type? What type of initiative we are going to take? What is the mitigation step we are going to take to avoid that kind of hazard? Then there comes the risk communication. So this is a crucial step. Once we identify which is the effective measure, then we have to communicate to the public after deciding the effective measure to avoid the particular hazard. So a risk analysis involve all the three steps, which is hazard identification, risk assessment, risk management, and risk communication. So right answer is all of the above. Next, what is the full form of NOAEL? The right answer is no observable adverse effect level. So what is this NOEL is? This is a threshold limit above which it can be a hazardous substance, and up to this limit that substance is considered as non-hazardous. So this is a threshold level fixed for each and every component, especially for the air pollutant components and water pollutant components. Next. We have solved many problems of this kind in the week 1 session, and this is a solution for week 1 assignment. So again, we are repeating it. If a compound X has an octane water partitioning coefficient of 130 and the concentration of X in lake water is 0.5 mg per liter, find an approximate concentration of X in the animal at the bottom of all food chains in the lake. So the question is to find the concentration of the particular compound in the animal. So here we are going to find the concentration in the component of the environment. So here in the lake water, the concentration is 0.5 mg per liter and the K partitioning coefficient is 130. So we know the formula, which is a bioconcentration factor formula we know. So bioconcentration factor is the concentration of X in the organism and the concentration of X in the environment, right? So before finding the concentration in the organism, we need to find this bioconcentration factor that can be obtained using this logarithmic formula, which is log BCF is equal to 0.79 log of KOW. K is the partitioning coefficient. Here OW is the octane water partitioning coefficient, which is 130 minus zero point 0.4. So if you solve this one, you will obtain the value of BCF. Once the BCF is known, the formula for BCF is concentration of X in the organism divided by concentration of X in the environment component. Here, the environment component concentration is 0.5 mg per liter, which is in the lake water. So now, if you are multiplying the BCF with 0.5, you will obtain the concentration of X in the organism, which is 18. Uh, yes. Okay. So the concentration is 9.31 mg per kg. Next question is match the following with a correct definition. We have discussed this in earlier sample questions. So, anyone having the doubt? Did anyone raise your hand? I'm hearing a sound repeatedly. So you have to match the correct definition of community, species, and ecosystem. So we all know that community is the assemblage of different population that live together, and species is the collection of group of similar organisms that can breed and produce a fertile offspring, and ecosystem is the collection of organisms that live in a place with the non-living environment. So it includes both living and non-living components. So the right answer is 3, 2, 1. So now we have discussed the week 1 solutions. Do you have any doubts in the assignment 1 solutions? Okay. We will continue to week 2 solution. So some substances break down, that is degrade by natural processes into different simpler substances. So we have discussed that whatever the pollutants present in the environment can be, that concentration of the pollutant can be reduced by 4 steps. The concentration of the pollutant can be reduced by either by the dispersion, dilution, or deposition or degradation. We know that dispersion is mainly for the air pollutant. So whenever a small concentration of pollutant is mixed with a higher quantity of air in the atmosphere, that pollutant is getting dispersed. Next is the dilution. So dilution here is whenever a fluent containing a higher concentration of pollutant is again diluted with water, means the concentration of the pollutant is going to get reduced. Next is the deposition. Deposition is by settling down slowly, that pollutant concentration is going to be reduced from the running water. Next is the degradation. So degradation is a process in which all the organic matter is going to be biologically converted by the microorganisms, or after some period of time through extreme pressure conditions in the environment, they will automatically degrade and stored as the organic carbon in the soil and environment. So here the question is breakdown of substances by the natural process. So the right answer is degradation. Among all these steps, degradation is the slowest process and it will take a lot of time. Uh, that is the right answer. Next question is find out the air to fuel ratio required for complete combustion of liquid fuel. The average formula, this is the molecular formula of the liquid fuel which is to be combusted, which is C6H13. So the liquid fuel is going to be combusted in an internal combustion engine and the air fuel ratio is asked. So to find this one, first what we need to do is we need to balance the equation. To entirely combust the liquid fuel, how much moles of oxygen is required? And oxygen is not directly given as the pure oxygen in this combustion process. They have asked for the air to fuel ratio. So we are supplying air to combust the fuel. So air typically contains both oxygen and nitrogen. So the reactant components include the liquid fuel C6H13, O2 and N2. Next, what are the product components? So here in the fuel is made of hydrocarbon, which is hydrogen and carbon. When carbon is combusted, it is going to be evolved as carbon dioxide. When hydrogen is getting reacted with oxygen, it is going to come as water, H2O. And then here the nitrogen in the air is an inert component. It will not react, it will remain as the nitrogen itself. So the reactant includes the fuel and oxygen and nitrogen, and the product includes the carbon dioxide, water, and nitrogen. Now we are going to balance this stoichiometric equation, in which you have to balance the carbon first. You have 6 carbon in the fuel, so 6 carbon dioxide should be equal. And then uh, we have to balance the oxygen again. So in this one, 6 carbon dioxide is removed and 13 hydrogen are there. So 6.5 H2O should be released from this reaction. So here 6 into 2. So 12 oxygen is there and again 6.5. So 12 plus 6.5 is 18.5. So 18.5 amount of oxygen is there. So 9.25 oxygen is getting reacted. Now we know the moles of oxygen getting reacted. So the volume percentage of oxygen in the air is 21 and the volume percentage of nitrogen in the air is 78 percentage. So we are calculating the moles of nitrogen going to be reacted for this much moles of oxygen in the air. So now this equation is balanced. Then you are going to calculate the molecular weight of each and every component. And this is the formula to find air to fuel ratio. What is the formula? AFR is equal to mass of air required for complete combustion of the fuel divided by the mass of fuel. So now mass of air required means first we need to add both the oxygen and nitrogen. And moles of O2 used is 9.25 and the molecular weight of O2 is 32 plus moles of nitrogen used is 9.25 into 70 divided by 21, which is 34.35 into 28, which is the molecular weight of N2. Then divided by the mass of fuel, which is 6 into 12. 6 carbon is there, atomic weight is 12, and 13 hydrogen are there, and atomic weight is 1. So 9.25 into 32 is 296, and 34.35 into 28 is 962. And here, if you add all these things, the answer is 85. So after solving this one, we will get the value of 14.8, which is the AFR, air to fuel ratio, to completely combust the liquid fuel of molecular formula C6H13 in an internal combustion engine. So you will be having a similar type of problems in exams also, just by varying the molecular formula of the liquid fuel. We have also discussed for C6H14, C7H14 like this. The molecular formula alone can vary. You have to balance the stoichiometric equation, and using this formula, we can calculate the AFR. Next. Heavy metals, Hg, Pb, which is mercury, lead, cadmium, and chromium, are categorized as physical pollutants, chemical pollutants, microbiological pollutants, biochemical instability. So, what is the answer? Any idea how these heavy metals are categorized? Or heavy metals coming under physical, chemical, microbiological, or biochemical? Yes, chemical pollutants. So the right answer is chemical pollutants. Which of the following is often one of the root causes for the soil pollution? So we have discussed already what are the major causes of soil pollution in the week 2 itself. What is the right answer? Is it because of agriculture or excessive industrial activity or poor management system or all of this? Simple, you know, right? Just because of all of this. So in the case of agriculture, what happens? We use excessive amount of fertilizers and all the pesticides are going to be run off into the water and cause the water pollution. Similarly, it is going to decrease the fertility of the soil. So it is going to the major reason for soil pollution. Next is the excessive industrial activity. Because of dumping of excessive industrial waste, the soil is getting polluted. And poor management system is our municipal solid waste. However, the amount of waste generation is going to be increasing day by day, and all these waste are not mostly properly managed. So all these three are the major reasons. Next question is, which of the following is the major cause of visibility impairment? So visibility impairment, this is mainly caused by the air pollution, right? So, which component is responsible? Particulate matter, O2, carbon dioxide, or carbon monoxide? The right answer is particulate matter. We know PM 2.5, PM 10 are there. This particulate matter is classified into different categories based on the size of that particulate matter. Whenever these particulate matter are getting reacted in the atmosphere, it forms a smog. And because of the smog, what happens? Visibility impairment is happening. Next is, what is the name of the plume shown in the following figure? So this is the stack. From this stack, the plume is produced. So this is the pattern of the plume. From the pattern of the plume, you have to identify what kind of plume is this, whether it is a coning or looping, lofting, or fanning. The answer is looping. So uh, we can observe this image. So in this one, if you see, looping is like a loop. You can observe this is because of the unstable condition. And coning, you can observe this pattern. It will be similar to the cone. This is happening under the neutral condition. And this is the pattern for the fanning plume, and this is the pattern for the lofting plume. So you can see that it is closed by the inversion, enclosed by an inversion layer, and here the inversion layer is underneath the plume. These are the major differences because of this different kind of plumes are formed in the industries. And dash is a body of rock and sediment that holds the groundwater. The options are gasoline, road salt, aquifer, and groundwater. The correct answer is the aquifer. So this aquifer is a body of rock and sediment that is going to hold your groundwater. We have solved many problems based on this. Next question is, which of the typical value of porosity of clay and fine sand? Generally, when there is a clay and fine sand, what is the porosity? They are asking. The right answer is 55 percentage of clay and 45 percentage of fine sand. These are the answers. So now, next question is a problem. First I will read the question and we'll solve it. So here the question is stating as CO2 carbon dioxide is emitted from a 75-meter high industrial chimney of diameter 0.25 meter to the atmosphere. Pressure is 1 bar on a clear summer day. Wind speed at 10-meter height from the ground is 4 meter per second. Calculate the effective stack height. Assume B characteristicity. P value is given as 0.15 and the stack gas velocity is 7.5 meter per second, and the temperature of stack gas and the ambient air at 80 meter is 50 degrees Celsius and 25 degrees Celsius. The question asked is to calculate the effective stack height, which is the capital H. So the question is very clear that carbon dioxide is going to be emitted from the industrial chimney uh, that is of a height of 75 meter, and the diameter of the chimney is 0.05 meter, and this is happening under the pressure of 1 bar, and the wind speed from the ground level is 4 meter per second, and it is given like it is from the ground only 10-meter height is there. And then calculate the effective stack height they are asking, and they have also provided the stack gas velocity, which is 7.5 meter per second, and the temperature of both stack gas and ambient air is also given. So now we are going to use this formula, which is delta H, Poland's formula, which is delta H is equal to stack gas velocity, then D is diameter of the chimney divided by U. U is the again velocity, and plus 1.5 plus 2.68 into 10 power minus 2 into P. P is the pressure. Ts minus Td by Ts. Ts is the stack gas temperature, and Td, it is not Td, it is Ta. Ta is the ambient air temperature, and again here D is the diameter of the industrial chimney. So D is the diameter of the chimney. So here we can calculate the delta H using this formula. For this, we already know what is Vs. So Vs is stack gas velocity. So at the height of 10 meter, it is 4 meter per second, and here the stack gas velocity is 7 point. Right, it is already given. Vs is 7 point. Next is the diameter. Diameter is also given, which is 0.25 meter. And then pressure is 1 bar. So 1 bar, so we are substituting 1 bar is equal to 100 kPa. So it is 10 power 2. Next is Ts and Td. We know 50 degrees Celsius and 25 degrees Celsius. To convert it into Kelvin, we have to add it by 273. So it is 323 and 298 Kelvin for Ts and Td respectively. Next again D is known. The only unknown value is U. U is again the gas velocity. So we already know at the height of 10 meter it is 4 meter per second. So at the stack height, what is the velocity? We need to find the U2. So U2 is equal to U1 into Z2 divided by Z1 whole power P. So here the P value is already mentioned, and we are going to assume it as a P category stability. So the value is 0.15. And Z2 is we need to find at the height of 75 meter, and already at 10 meter height we know 4 meter per second. So if you solve this one, you will obtain the U2 value as 5.41 meter per second. And then you have to substitute all the obtained values in the delta H formula. So 7.5 Vs into 0.25, the diameter of the chimney, divided by U, the velocity at 75 meter height, which is now derived using the second formula, which is 5.41 into 1.5 plus 2.68 into 10 power minus 2 into pressure is 100 kilopascal into Ts is 323 and the Ta is 298 divided by 323 into 0.25. So the right answer is 0.537, and already it is given like at the height of 75, right? So with the 75 you need to add this 0.537 to obtain the effective stack height. I think the answer is different in the weak solution, but the right answer is 75.537. You need to add both these two. The right answer is this one. Do you have any doubt on this problem? It's very simple. If it is 3.8, you will get this answer 75.566. But here the question is changed to 4 meter per second. So the right answer is only 75.537. Any doubt in that problem? Match the following are associated with their categories of pollution. So you have to match these following. Sewage is going to cause, absolutely, it is going to cause water pollution. All the sewages are treated in the STP and again discharged into the running waters. When these sewage water are not treated up to the level, it is going to pollute the water. Next is the particulate matter. So particulate matter, they will be causing the air pollution. Mostly this particulate matter are going to be emitted from the thermal power plants, coal power plants. Next is loss of hearing. And the loss of hearing is because it's going to cause the noise pollution. So because of noise pollution, loss of hearing is going to happen. So sewage is related to water pollution, so answer is 2. And particulate matter is related to air pollution, answer is 3. Loss of hearing is related to noise pollution. So answer is 2, 3, 4. So we have discussed the solutions of week 1 and week 2 assignments. We have already seen the overview of week 1 and week 2 lectures in the previous week, and we have solved the sample problem and the sample question. And today we have discussed the week 1 and 2 solutions. Now we will go into the brief of this week 3 lecture, and we will discuss the sample questions for week 3, and then we will solve the problems. So this is the overview of lecture 11. So in this week 3 content, this is mainly focusing on this week 3 content mainly focuses on the different kind of pollutant and their standards, and what are the instrumental techniques which is going to measure these kind of environmental pollutant. That is the content totally covered in the week 3. So now in the lecture 11, the first topic is going to deal with the ambient air quality and air quality and standards. So if we see in the case of air quality, mainly two pollutants are there. The first one is the primary pollutant and second one is the secondary pollutant. Primary pollutants are produced directly by the combustion of fuel. So these are the emissions from the power plants, mainly because of combustion of the fuel. All these SOx, NOx, carbon monoxide, carbon dioxide, the particulate matter, and some of the heavy metals like lead are going to be emitted in the form of fly ash also. So next is the secondary pollutant. So secondary pollutant, this is formed by the interaction of the primary pollutant with the air components. So again, because of this interaction, it's going to generate the secondary pollutant, which is acid rain and smoke. Next category is the water quality standard. So coming to the water quality and standards, we already discussed in the water pollution topic what are the different kind of pollutants are there. So if we see how the physical components are polluting the water means TSS. So TSS is the total suspended solids. So the TSS is going to mainly affect the turbidity of the water because of the suspended solids. Next is the TDS. TDS is the total dissolved solids. Next is the temperature. Temperature is water is getting affected. Next, taste, color, odor. All these parameters are coming under the physical categories. These are all going to change the water quality. So in the case of solids, mainly the total solids is classified as the TSS and TDS, and the one more kind of total solid is the total volatile solids. Next is the chemical. In this chemical category, it includes the BOD, COD. BOD is the biological oxygen demand. COD is the chemical oxygen demand. So these are the oxygen demand, like how much amount of oxygen is required in that water to degrade the organic components present in the water. Is measured by these terms, BOD and COD. Next is the nitrogen, phosphorus, heavy metals, and total organic carbon. How these parameters are going to be present in what range? So if BOD is higher, COD is higher, that water is suitable for what purpose? Whether it is it can be used for irrigation, or it can be used for cleaning and washing, or it can be used for drinking. All the uh, standards are fixed based on these parameters only. Next is the biological component. So in the case of biological component, we will see the aquatic organisms and then the pathogen. Pathogen are the major component. Here, how much amount of microbes are there? That is all the sewage waters after being treated or discharged only into the river bodies, right? So in the river bodies, these pathogens are measured mainly by using the E. coli, Escherichia coli, which is one type of bacteria, coliform. We use that bacteria as an indicator to measure the human pathogens present in it. Next parameter we are going to discuss is the ion balance. So why this ion balance is very important means all the excess amount of ions present in the water will also affect the nature of the water. Mainly these ions include the calcium, magnesium, and then sodium, potassium. These are the major ions which is going to deteriorate the quality of the water. So, and other ions includes the carbonates and bicarbonates. So, if we see the ions, they are mainly classified into two types, cations and anions, one of which is positively charged and the others are negatively charged. So, we are going to calculate the error percentage in this cation and anion balance. Like there should be a balance between cation and anion in the water. For every five cations present in the water, the same ionic strength of the anion should also be present. How much percentage there is a difference in this balance is going to affect the quality of the water. So this can be calculated by using this formula, percentage balance error, which is obtained by subtracting the summation of cations and anions and divided by the addition of cations plus anions into 100. So this error percentage should not exceed 5 percentage. Then only it can be used. That water can be used. Next important parameter of the water is the hardness. So if you see the hardness, this hardness is mainly uh, measured in terms of the amount of carbonates present in it. And then it includes carbonate and non-carbonate. When this non-carbonate is present at the higher amount, then water treatment is very difficult. When the carbonate content is less or high, it is not a problem. When the non-carbonate contents are higher, it is very difficult to treat them. Because this hardness is also called as temporary hardness. When this water is boiled, all these carbonates can be evolved as gas. So this water can be easily treated. When the amount of non-carbonates present in the water is higher, like the salts is very much higher means, then that kind of water will have a permanent hardness. It is very difficult to treat. So before treating the water and before categorizing the water into different qualities, we will be measuring all the physical, chemical, biological parameters, and mainly we will check the ionic balance and the hardness of the water. Coming to the lecture 12, it is also speaking about the environmental quality and standards. And here, designated best use class of surface water. So the surface water is classified into five categories: A, B, C, D, E. You can look in detail in the lectures. A, B, C, D, E. Some of them can be used for domestic purpose. Some of them can be used only for the industrial purpose, like that. They are classified based on the range of all these components present in the water. In this one of the important terms is sodium absorption ratio. This is used to evaluate the suitability of water for irrigation, whether that water is helpful for irrigation or not, can be used or not. Why this parameter is very much important means the salt content can affect the growth of the plants very much. So when the electrical conductivity of the water is too much higher, it can cause the salt stress in the plants. So that Because of that salt stress, plant cannot uptake all the essential nutrient present in the soil, and it cannot grow properly. So always it is very important to measure the SAR, which is the sodium absorption ratio, before using the water for irrigation. In this one, we will calculate the amount of sodium, calcium, and magnesium ions, and the formula is SAR is equal to Na plus divided by square root of calcium plus magnesium ions divided by 2. You have to remember this one. Next, problems induced with sodium induced dispersion. Whenever a higher concentration of sodium is there in the water, what kind of problems will be existing means reduced infiltration. So the infiltration of water in the rocks is very much difficult, and then the hydraulic conductivity also decreases, and then the surface rusting. What happens is the surface area wherever this water is used, like in industries, when these waters are passing through the pipes, uh, what happens? It will be rusting all the pipes. So the property of the water changes. It will cause these much problems in the applications. Next important term is the sodium percentage. Since the sodium can induce these many problems, sodium percentage is another formula to calculate it, which is equal to Na into 100 divided by summation of sodium, potassium, calcium, and magnesium ions. One important thing is this sodium percentage should not exceed 60. Then only that water can be used. The industrial effluent standards are included. In this one, the quality and quantity of generation is considered, and based on the each steps involved in the particular industry, different kind of standards are set, and the major classification includes the general emission standard, which includes the emission criteria from that industry, mainly dealing with the air components. Next is the equipment-based standards. Like I said, for the particular kind of equipment, what grade of water can be used, like that we need to check. Next is the load-based standard. Load or mass-based standard include how much volume we are using, like how much amount of water we are using, how much amount of the particular component we are using based on the these are categorized. Next is a concentration based concentration. It is classified based on the concentration. Next is noise pollution standards. So noise pollution standard means based on the territory. It depends on the area also. Like for the working zone, there will be a different standard. For schools, there will be a different standard. Like that, based on the zone, the standards are classified into A, B, C, D categories. The next one is the vehicular pollution standards. Like this what kind of vehicle can emit up to what percentage of carbon dioxide, like that. Based on the vehicle type, there are pollution standards. For more detail, you can look into the lecture videos. Next, coming to the lecture 13. Lecture 13 and 14 mainly deals with the type of instruments being used to analyze these environmental pollution level. So the first one is environmental analysis. So what is environmental analysis means? This is the analysis of naturally occurring chemicals and anthropogenic contaminants. So anthropogenic contaminants or the man-made pollutants. So here the qualitative determination, quantitative determination of them. First thing is quality. Qualitative means it is to detect the element, like whether that substance is present there or not. So it is just qualitatively confirmed. Next is quantitative analysis. In the case of quantitative analysis, we are measuring the particular component at what quantity, whether this much mg of the component or this much ppm of component is present in that compound. Like that, we are quantitatively measuring it. Next is instrumental analysis. So instrumental analysis is used here. We will be using an instrument for both deduction and quantification. So coming to the instrumental analysis, there are different instruments used for measuring different kind of pollutants. Some of them are discussed in this lecture. Now, among this, the first one is the electrochemical methods. So, the electrochemical methods include the pH, conductivity, and dissolved oxygen. This is mainly to measure the property of the water, how much pH is there. So, pH will be dealing with the amount of H plus ions present in the water using the electrode. Next, conductivity. Conductivity you will be obtaining in millisiemen per second or microsiemen per second, like that you will be obtaining the conductivity of each water. Why conductivity is very important means we already discussed, like the salt stress is very much uh, important important to be considered before the water is used for irrigation purposes. Mainly to measure the salinity of the water, the conductivity is measured. Next is the dissolved oxygen. Dissolved oxygen is very important because of that only there exists the uh, chemical oxygen demand and biological oxygen demand. Next is the chromatographic separation technique. Uh, there are different types of chromatography. Among this, the first one is the GC. GC is the gas chromatography. Next is the HPLC, high performance liquid chromatography. And one of the category is the ion chromatography. HPLC is further classified into many types. So we will discuss this later. Next is a spectrophotometric analysis. So here in the case of spectrophotometric analysis, based on the color development or based on the radiation, only the spectroscopy methods are used. One of them is UV visible spectroscopy, FTIR spectroscopy, and AES is the atomic absorption spectroscopy. And other instruments being used are X-ray diffraction, thermogravimetric analysis, and BET to measure the surface area of the particular component. So these are the other instruments being used to measure the environmental pollutants. Coming to the chromatography method, this gas chromatography is mainly used to measure the volatile component. So whatever components are non-volatile in nature cannot be measured in the gas chromatography. That is the main thing. So here, what is the output means based on the retention time. So there will be a retention time. So you will get a response, like you will get a peak. So each peak is giving the concentration of the particular component and what type of component can be analyzed using the library. Next is the HPLC. So HPLC, as the name indicates, it is the high performance liquid chromatography. For the liquid components, you can measure the uh, type of substances present in it. It is further classified as the normal phase, reverse phase, ion exchange, and size exclusion. So here in the normal phase, what happens is the column is polar in nature, and the mobile phase is non-polar in nature. But in the case of reverse phase, the column is non-polar in nature, and the solvent used is polar in nature. And in the case of ion exchange chromatography, again there is cation exchange chromatography and anion exchange chromatography. To elute the cations, you will use cation exchange, and to elute the anions, you will use the anion exchange chromatography. Those are based on the surface charge of the substances present in the component. Next is the size exclusion chromatography. This is also called as the gel chromatography. Here the separation is mainly based on the size. So if you consider a column here and the component of larger size, these are the packing present in the column. So whatever getting packed in a column is called as a stationary phase. The stationary phases are stagnant, that is, it is very solid. And the mobile phase is the movable one. Whatever liquids we are passing through this chromatographic column are called as the mobile phase components. And the column is stacked with different materials like silica, cellulose, like that. So here we will be passing the substances. So what happens here? This column is tightly packed, right? So when the substance is larger in size, larger the particle, it gets eluted first. So larger particle first, it will come out first, and then the smaller particle will penetrate in between the pores of these beads, and then they will come at last. So the smaller particles will come later on. So based on the size only, the particles are getting separated. Now coming to the lecture 14, what is spectroscopy? Spectroscopy is the study of properties of matter through its interaction with different types of radiation. So here the major type of radiation is the electromagnetic radiation. And in the case of UV visible spectroscopy, only in the visible and UV region we are going to analyze the components. So this UV visible spectroscopy is mainly used to determine the quantities of analytes in the sample, how much the substances are present, how much concentration is there in the sample. And this is based on the Beer-Lambert's law, which is given here. Logarithm of I naught divided by I is equal to epsilon L dot L into C, or we know that epsilon is equal to A divided by C. Here I naught is the intensity of incident light. So here, whatever light is passing through the cuvette is the intensity of incident light, and whatever is passing out of the cuvette is the intensity of transmitted light. And then the molar objectivity, this is constant for each thing, and L is the path length. So usually the path length is the cuvette size. Most commonly used one is 1 centimeter. And then C is the concentration of the sample. What is the concentration present in it? Next is A is the absorbance. So absorbance is directly proportional to this concentration. Next is the FTIR. So FTIR is the Fourier transform infrared spectroscopy. It is used to create the fingerprint of the chemical. So whatever the chemical present in the particular component, each chemical will be having a different kind of fingerprint that will be observed only at the particular wavelength. Using that only, we will determine what type of components are present in that particular sample. So here we use the infrared radiation to determine the fingerprint of the chemicals. Next, we use the Fourier transform law to convert the frequency range, and we are measuring it in the wave number. So here we will be having a graph of transmittance percentage and the wave number. So the peaks will be based on the vibrations of the molecule. Like this, different vibration will be there. So each vibration will belong to a particular wave number, and the double bond carbon groups, alkane, alkene, hydroxy group. So each chemical group will have a fingerprint which will exhibit only at the particular wave number. And based on the library, we can measure what type of component is there. So some of the working images I have given here for the instruments we have discussed so far. This one is about the HPLC. As we discussed, the HPLC is the high performance liquid chromatography. Mainly it is using the liquid samples. So here we are passing the solvent through the HPLC pump. So the mobile phase is the solvent here. So mobile phase is a substance which is going to carry our sample. So the sample is going to be dissolved in a solvent, in a liquid one. Okay. The solvent is getting pumped into the column. Before that, before the pump and the column, there is an injector. This is the important component. So in this injection port only, we will be injecting our sample. So what happens here is our sample is getting mixed with the solvent, and it is being carried away through the solvent. So only it is called as the carrier. Now it is going into the HPLC column. So here the HPLC column is of different types. We have discussed it. It can be a normal phase column, reverse phase column, ion exchange column, or a size exclusion column. But the principle is same. So in the stationary phase, what happens? The sample is going to react. This sample is going to pass through the column based on the size or affinity to the column. The sample is getting eluted, and then there comes the detector. So in the detector, which component comes first, like that, the detector is going to determine, and the peak is obtained. Based on the retention type and the peak area, we will determine what component is that, and that component is presented, what quantity is also can be determined. This is a this requires a technical skill to measure the particular component. It is very accurate, but it is also costly. So the results will be very accurate, but this is very costly analysis. Next, this is the gas chromatography working component. So here the mobile phase is the carrier gas. That is the major difference. So a mobile phase is the one in which our sample is getting carried away to the stationary phase. So in the HPLC we use the solvent as a mobile phase, and in the gas chromatography we use the carrier gas. Mainly we use the helium gas most commonly, and then we will control the flow rate of this gas, and there will be different traps to remove the dust and all. Then we again have a auto sampler. So this is where we are going to inject our sample, and that sample is getting carried away in our mobile phase. Okay. Now it is entering through the inlet port, then it is going into the column. So this box is the column oven. So why here oven is used means here the main principle is either based on the affinity or based on the size, it is just getting separated. Here we have the column oven to evaporate our sample, like to burn our sample. Only the volatile substances can be measured in the gas chromatography because of this. So at particular temperature, our sample will get evaporated, and it will be separated into smaller particles, smaller volatile compounds. And based on their affinity to the stationary phase column, and based on their nature of mobility, these particles are getting separated, and it is being detected, and it is obtained as the chromatogram. Chromatogram is the graph in which the peaks are visible. Mainly this chromatograms between the retention time and the percentage. So from this different peaks are obtained, we will measure this peak area. Each peak correspond to a particular type of compound, and with that we will identify what kind of compound is that, and using this peak area we will find how much concentration of a particular compound is there in our sample. So this is gas chromatography working mainly on volatile compounds only can be used in gas chromatography. And this is the working of the UV visible spectroscopy. In this one, a lamp is there. So this lamp is very important for heating. And then from the lamp only, that electromagnetic radiation is passed, and the UV visible region is being absorbed. And using the monochromator, the particular wavelength is fixed. Like say for example, we are measuring at the 420 nanometer. All kind of wavelength will be emitted from the lens. The monochromator is going to fix the particular wavelength, and at the particular wavelength, the light is passed through the cuvette. This in the cuvette, we are pouring our sample, and how much intensity of radiation is getting absorbed by the sample, and how much is transmitted. All these are measured by the detector. and this signal is amplified, and this signal is read out as the absorbance A. And we have a graph of absorbance for the particular nanometer, and based on the absorbance only, we know that how much concentration of the particular compound is there. And this is a working of the single beam spectrophotometer. And if we have double beam means there will be two different things. Like this lens will be there for the reference, and lens will be there again for the sample. So in the single beam spectrophotometer, what happens is we will keep the blank in the cuvette, and we will set as 0, and then we will measure the absorbance. Then again we will take the blank out from the cuvette region, and again we will add our sample in the cuvette and place it here. So first time itself we are nullifying the value as 0 using the blank. Next you will be continuously taking reading of the samples. If there are any impurities in between, and uh, there is a fluctuation in the value, again we need to pour the blank in the cuvette, keep it again and set blank as 0. Again we will pour the sample. But in a double spectrophotometer, what happens is there will be always a blank for each and every reading. So there is a reference cell and there is a sample column also. So for these two, there will be a light passing. Say for example, 420 nanometer will be passed here and 420 nanometer will be passed here. At a time, both are passed, and this value is being subtracted from the sample value and the absorbances of time. So for each and every sample, the blank is subtracted from the sample value. So this will be having higher accuracy than the single beam spectrophotometer. That is the major difference. And coming to the fourth figure, this deals with the FTIR. So in this FTIR, based on the samples, different methods are there. Like FTIR can be used for the solid samples, and FTIR can be used for the liquid samples. For some kind of samples, it means the preparation of the sample. Like some samples should be converted to solids, and some should be pelletized before analyzing. Some can be directly placed over the crystal, and analysis can be done. So, what is the basic mechanism happening in this FTIR is there will be two different mirrors. So, here the light source is the infrared. Infrared light source is used, and then here we use the deuterium lamp. Mainly, the deuterium lamp is here. Here, the light source is the infrared light source. So, this light source is passing through two different mirrors. One is the sliding mirror, and another one is the fixed mirror. Beam splitter is there, and then we will be placing the sample over a crystal here. Based on the reflection and refraction, the sample is going to emit some amount of signal to the detector. So in the detector, the particular fingerprints are measured, and it is converted using the Fourier's law, and like this different patterns of fingerprints will be absorbed for the particular for the particular wave number. This is the working of the FTIR. So far we have seen the brief of lecture 11, 12, 13, 14, which mainly deals with the environmental quality and standards and the instrumental techniques used to measure the environmental quality. So, do you have any doubt? Do you have any doubt? Okay, now we will see some sample questions of week 3. The first one is match the characteristics of water with their cause. So here it is a match the following. These are the different characteristics like color, turbidity, and dissolved solids. What are the causes it is going? What is the cause for the change in this characteristic we are asking? First one is it's because of the suspended solids. Next, it is because of the minerals of calcium and magnesium. Next, it is because of decaying vegetation or industrial effluents. Anyone knows the answer? Anyone knows the answer? Okay. The answer is due to the decaying vegetation or industrial effluents, the color of the water is changed. Whenever the industrial effluents, say for example, the effluent is from the textile industry. Most of the azo dyes are non breakable, so it will not degrade. So the color of the water will get changed. Next is turbidity. Turbidity is mainly because of the suspended solid. All the solid matter will hinder the uh, passing of light through the water. So it causes the turbidity. Next is dissolved solids. These characteristics will change because of the minerals of calcium and magnesium. Mainly, it is caused by all types of minerals. If you see, we are having a water sample. First, we will be filtering this water sample. So, when this water sample is filtered using the filter paper, whatever the particles being present in this filter paper are called as the suspended solids. So the suspended solids are mainly separated just by filtering it or passing it through a grid chamber. So whatever water is passed through this filter paper will contain the dissolved solids. So all these dissolved solids mainly contains the minerals and ions. So that is what causing the characteristic change in the water. So the right answer is 312. What is the permissible pH range for the drinking water? So, a drinking water should be of what pH? 8.5 to 10, 5.5 to 7, 3 to 6.5, 6.5 to 8.5. What is the answer? 8.5 to 10. So, we know the pH scale, right? We know the pH scale. So, it is 0 to 14. The middle one is 7. So whatever above 7 is basic in nature. Whatever below 7 is acidic in nature. Right. So 8.5 to 10 it is alkaline in nature. 5.5 to 7 is slightly acidic. And 3 to 6.5 is extremely acidic. It is in here. And 6.5 to 8.5 is not, it is here. Right. It is either neutral or it can be slightly basic and very slightly acidic. So the right answer is 6.5 to 8.5. This is the permissible pH range for drinking water. Next, the suitability of water for irrigation purposes is evaluated by using the sodium absorption ratio, SAR. The correct relation for SAR. We have discussed this earlier itself, right? This is very important before deciding whether that water can be used for irrigation or not. It mainly involves the calculation of amount of sodium, calcium, and magnesium. But what is the formula? The right answer is SAR is equal to Na plus divided by square root of calcium plus magnesium divided by 2. This is the right answer. Which of the following compounds cannot be analyzed in gas chromatography analysis? Compounds that do not vaporize, highly reactive compounds, low molecular weight compounds, both A and B. Any guesses? What is the answer? Which compounds cannot be analyzed in gas chromatography? The answer is both A and B. Compounds that do not vaporize. That is obvious, right? This is a gas chromatography. Only the gaseous components can be measured. So whenever the component is not vaporizing, that component cannot be measured. And then the second one is highly reactive compound. For all the case of chromatography, this is considered. Whenever the particular compound is going to react with the stationary phase column, that compound cannot be measured. Either it can be a gas chromatography, it can be a liquid chromatography. In the case of chromatography itself, when the component is going to react with the column, that component cannot be estimated. So answer is both A and B. Next, match the type of HPLC with their specifications. So we have different columns in HPLC, which includes the normal phase, reverse phase, and an ion exchange. Match the following. Anyone knows the answer? Okay, the right answer is 213. So normal phase, we have discussed like normal phase uses the column of polar nature. So the column is polar and the mobile phase is non-polar in the case of normal. And reverse phase is just opposite. So the column is non-polar and the solvent is polar. That is miscible solvent. Okay. Next, ion exchange. The column contains the ionic groups. Can be a cation or anion. And the mobile phase is buffering agent. Based on the buffer strength, the particular cation or anion can be separated. If we need the cation to be separated, we use a specific buffer of particular anions. If we need to separate the anions in the column, we will use a particular ion strength buffers. So based on that, mobile phase will also vary. So the right answer is 213. Next question is, which of the following is the disadvantage of HPLC analysis? Efficiency, accuracy, cost, all of the above. Efficiency and accuracy are the advantages of HPLC. Cost is the only disadvantage of HPLC analysis. Next, dash is the study of the properties of matter through its interaction with various types of radiation, which is mainly electromagnetic radiation of the electromagnetic spectrum, which uses the properties of matter through its interaction with the radiation. Spectroscopy, gas chromatography, HPLC, or none of the above. What is the answer? Based on the radiation mix. Voice is not. Am I Am I audible now? Is it okay? Okay. So, which is the study of properties of the matter through its interaction with various types of radiation means answer is spectroscopy. Because we know in the gas chromatography, gaseous components are separated based on the affinity and size, and in the HPLC, the liquid components are separated. Here, it is mainly based on its affinity and size, and also the interaction, the two column. But spectroscopy is based on the type of radiation, and it also depends upon the interaction of the particular matter with the radiation. What is the full form of FTIR? You know that. FTIR stands for Fourier transform infrared radiation. UV visible spectroscopy is based on which law? Beer-Lambert's law, Newton's law, Fourier law, or Fick's law? It's based on Beer-Lambert's law, right? So it is relating the absorbance with the concentration. Next, mole fraction of aqueous glucose solution is 0.035. So this is a problem. The mole fraction of glucose is given, which is 0.035. What is the molar concentration of glucose? So the molar concentration of glucose is asked, and the density of the solution is asked to be assumed as 1. The answer is 2.015. So we'll see the solution. So initially the mole fraction is given. So this is a binary solution. It consists of only glucose and water, right? So first X glucose 0.035, and the density of solution is asked to be assumed as 1 gram per ml, and the mass of the solution. So since the density is 1, the weight of the solution and volume of the solution is same, right? So it is 1000 grams. So first we need to find the moles of water. Why we need to find the moles of water means we are going to calculate this molar fraction. Molar fraction is equal to mole of glucose divided by mole of glucose plus mole of water, right? So we need the mole of glucose. So we need to find the mole fraction here. Sorry, the mole fraction is given. We need to find the moles of water. So to find the moles of water, we know what is the mole formula? N, small n is a mole. Number of moles is equal to weight by molecular weight. So here the weight is 1000 gram, and the molecular weight of H2O. That is the molecular formula of water. H2O, right? H is 1, O is 16, 2H are there, so 18 grams. So 18 gram per mole is the molecular weight of water. So if you divide 1000 by 18, the answer is 55.56 moles of water. So you know the molar concentration is mole fraction is 0.035, and 55.56 moles of water are there. And we are rearranging the equation. So 0.035 N glucose plus into moles of glucose plus 1.9446. If you multiply 0.035 into 55.56, you will get 1.9446 is equal to this one, moles of glucose. So you rearrange this equation. So you subtract 0.035 from 1, you will obtain 0.965 moles of glucose, which is equal to 1.9446. So you need the N glucose, which is 2.015 moles. That is the answer. Okay. Do you understand this problem? Any doubts in this one? First, the mole fraction is given and the moles of glucose is being asked. So the mole fraction is equal, formula is mole fraction is equal to moles of glucose divided by mole of glucose plus mole of water. So we are finding the mole of water and then we are rearranging the equation and calculating the moles of glucose using this equation. Okay. Okay. I hope no doubt is there. Now we will solve some tutorial problems. There is a similar problem in your tutorial question, uh, which asks the which gives the mole fraction of the aqueous glucose solution is 0.025. Earlier it is 0.035, right? So in this question it is 0.025. What is the molar and mass concentration of the glucose? And here also the assumption is given as density of the solution is equal to 1. So please solve this problem in similar way. Everything is same. Instead of 0.035 in the question, it is given 0.025. So you have to substitute 0.025 instead of 0.035. Please solve this problem in the similar way and tell me the answer. Have you solved this? Have you solved this one? So the answer is 1.42 moles per liter. So if you solve this in similar way, you will obtain n is equal to, if you subtract 1 minus 0.025, it is 0.975, and here you have 1.389. If you multiply 0.025 with 55.56, you will obtain 1.389, and then you will obtain N glucose as 1.424. Okay, and then the second question is, what is the mass concentration of glucose? We have found the molar, what is a molar of glucose, and then what is the mass concentration of glucose is asked here. To find the mass concentration, what you have to do is first you need to calculate the molecular weight of glucose. So the molecular formula of glucose is C6H12O6. So atomic weight of carbon is 12 and hydrogen is 1, oxygen is 16. 12 into 6 plus 1 into 12 plus 16 into 6. So totally we will get 180, which is the gram of glucose. Now to find the mass concentration, you have to multiply 0.025 gram with this 180 and you have to divide it with 17.55. So the 17.55 is the gram of water and 0.25 grams of glucose is 0.25 grams of glucose is there. That is given. So your mass concentration is 256 gram per liter. So using the mole fraction, we have found the moles of glucose present in the solution. And to find the mass concentration of only the glucose, you need to first know the amount of glucose present. So the molecular weight into 0.025 is the amount of glucose present in the solution divided by amount of glucose in the water, together is 17.45. We divide the amount of glucose by amount of glucose in water, the mass fraction is 256 gram per liter. The next question is find out the DU, which is dissolved oxygen in aerated water at 25 degrees Celsius. So the temperature is already given in a treatment plant. KH. What is KH? KH is the Henry's constant. So the Henry's law is relating the concentration of the oxygen with the partial pressure. Okay. So the Henry's constant of O2 at 25 degrees Celsius is given in the question itself, which is 1.26 into 10 power minus 3 m per atmosphere. So now 1 molarity of O2 is equal to 32 gram per liter. Okay, this is also given. Now what you have to find is you have to find the amount of dissolved oxygen, which is nothing but the oxygen concentration. So you need to rearrange this equation, which is KH is equal to O2 divided by PO2. So you need the O2, so KH into partial pressure. So KH is standard for the 25 degrees Celsius, which is 1.26 into 10 power minus 3. And the partial pressure of oxygen in the atmosphere is 0.12. This is also standard. So you need to multiply this 0.21 into 1.26 into 10 power minus 3. Now the atmosphere and atmosphere will get cancelled. Only the molarity is there. Now this molar concentration is there. So you need to multiply with the weight, which is 32 gram per liter, right? So this is 32 gram per liter. And finally, this value is converted into mg per liter. So again, you are multiplying it with 10 power 3. So the answer is 8.467 mg per liter. So the question asked is to find the DU. So if they are asking to find the dissolved oxygen concentration and they have given you the value of KH, we have to use the Henry's law. So using the Henry's law, we will obtain this equation. You can remember this equation, which is KH is equal to concentration of O2 divided by the partial pressure of oxygen. So either the concentration of oxygen can be given and they can ask the Henry's constant at a particular temperature, or they can give the Henry's constant at a particular temperature and ask you the concentration of the dissolved oxygen. Okay. Likewise, you have to rearrange and find the unknown component. Next. So the next problem is acetic acid or vinegar. Vinegar is another name for the acetic acid. And the molecular formula is CH53COOH. So this acetic acid is oxidized to carbon dioxide and water by microbial action. So the acetic acid is converted into carbon dioxide and water by the microbial action. A vinegar manufacturing plant has 50 mg per liter of acetic acid in its effluent wastewater. So the effluent wastewater contains 50 mg of vinegar, that is the acetic acid, uh, in per liter. The plant flow, so the flow rate is 500 meter cube per day. How much oxygen is required each day to oxidize the vinegar? Question is very simple. So you have an industry. Okay. So you have an industry. So from that industry, there comes the wastewater. The wastewater contains the acetic acid. This acetic acid only converted into carbon dioxide and water. So to completely oxidize the acetic acid to carbon dioxide and water, you need two moles of oxygen for every mole of acetic acid. Right. This is how you will balance the equation. And here, how many carbon are there in the acetic acid? Two carbons are there. So two CO2 will be liberated. So oxygen here is 4. And how many H are there? H3 and H. So 4 H are there. So 2H2O will be liberated. So here 2 into 2, 4. 4 plus 2, 6. Right. Already 2 oxygen is here. So here to balance it, you will put 2 O2. This is how we have to balance the stoichiometric equation first before doing the calculation. Okay. So now for every mole of acetic acid, 2 moles of oxygen are required to completely convert them into carbon dioxide and water. Okay. That is what given here. 2 moles of oxygen are required to oxidize the acetic acid, carbon dioxide and water, and amount of acetic acid oxidized each day. So this is for 1 mole of acetic acid. In the question, it is given like for every 1 liter of the effluent wastewater, it contains 50 mg of acetic acid. So there is a 50 mg of acetic acid per liter of water. So what they are doing here is they are converting this mg into gram. So we are dividing it with 1000. Okay. And then the flow rate of the effluent is 500 meter cube per day. So again you are converting the meter cube to liter. So 1 meter cube is equal to 1000 liter. So this is for conversion. So now we are converting this okay by dividing with 60 gram acetic acid. What is 60? Uh, that is the molecular weight of acetic acid. Atomic weight of hydrogen is 1 and the carbon is 12 and oxygen is 16. Right. With the atomic weight, we need to calculate the molecular weight of acetic acid, which is 60 gram. Okay. Then by solving this, you will obtain the amount of acetic acid oxidized each day in that plant. Okay, which is 417 moles per day. Since 2 moles of oxygen are required from the stoichiometric equation, we know that for every 1 mole of acetic acid, 2 moles of oxygen is required. Now we know 417 moles per day are there. So we are multiplying it with 2 moles of oxygen. So now we know that how much oxygen is required to convert the acetic acid per day, which is 834 moles of oxygen per day. And then the mass of oxygen is to find the mass of oxygen instead of moles. What we need to do is we need to divide, we need to multiply it with the molecular weight, which is 32 gram. Okay, then you will obtain 26,700 grams of oxygen is required per day. Here we are converting the gram into moles. So we are dividing it with the molecular weight. Here we are converting the moles into grams weight. So we are multiplying it with the moles. Okay. So finally the answer obtained is 26.7 kg of oxygen is required per day to convert 50 mg per liter of acetic acid, which is discharged in as the effluent wastewater at the rate of 500 meter cube per day. So the answer is 26.7 kg. Okay. Any doubt in this problem? Any question? So coming to the next problem. If 500 mg per liter ethanol, a biodegradable compound, is completely oxidized. Calculate the theoretical oxygen demand, chemical oxygen demand, ultimate biochemical oxygen demand, BOD5, TOC, total organic carbon, if KD is 0.023 per day. So here we are talking about ethanol. The molecular formula for ethanol is C2H6O. Okay, so this ethanol is biodegraded by oxidation process, and finally the product is ethanol comprises only what? Carbon, hydrogen, oxygen. The product will be carbon dioxide and water. Here again we need to do the stoichiometric balance. So we have two carbon, so two CO2 will be liberated, and we have six hydrogen, so three H2O will be liberated. So 2 into 2 is 4, 3. So 7 oxygen atoms are there. Already one oxygen atom is present in the ethanol. So 6 oxygen atoms are used for the oxidation, which is 3O2. So now the equation is completely balanced. Now you can observe that for 1 mole of ethanol, we require 3 moles of oxygen to completely oxidize it and to biodegrade into carbon dioxide and water. So for every 1 mole of ethanol, 2 moles of carbon dioxide is released and 3 moles of water is produced. To find the theoretical oxygen demand. Theoretical oxygen demand is the stoichiometric demand. Okay, we know that 3 moles of oxygen is there. To convert the moles into weight, what we have to do is we know the formula, right? N is the mole of a particular component. So mole is equal to weight by molecular weight. So we need to find weight. So we have to multiply moles with the molecular weight. So 3 into 32. O is 16, O2 is 32. Okay, 3 into 32 is 64. So you require 64 grams of oxygen for 46 grams of ethanol, right? For 46 grams of ethanol. So again, if you divide this one, we will obtain 2.09 mg of oxygen is required per mg of C2H6O. Okay, again, what is given in the question is we have 500 mg per liter of ethanol. This is for per mg of ethanol. For 500 mg of ethanol, we have to multiply this 2.09 into 500, and the answer is 1045 mg per liter. 1 mg per liter is equal to 1 ppm. So I can directly write it in ppm, 1045 ppm. This is the theoretical oxygen demand. Okay. Now we can assume that the COD and the theoretical oxygen demand and the ultimate BOD are same. Okay. So now we know the ultimate BOD and theoretical oxygen demand are same. We have found the value for the theoretical oxygen demand. For that, what? 2.09, right? So you can use this to calculate the BOD5. So in general, 5 days BOD is always measured for the calculation, and for any BOD at any time t, to calculate it, the formula is this. You can note down this formula. BOD at any time t is equal to ultimate BOD into 1 minus e power minus kt. Okay, already the value of k is given. Okay, degradation constant is already given. Kd is equal to 0.023. Okay, and the time here is they have asked you the BOD 5. So here the t is in this question. In this question, T is equal to 5. Okay. So BOD 5 is equal to 2.09 is your ultimate BOD, because the ultimate BOD is equal to the theoretical oxygen demand. into 1 minus e power minus 0.023 into t is 5. If we solve this, we will obtain 0.23 gram of O2. Okay, this is again for per gram of ethanol. And the question is talking about 500 mg per liter of ethanol. So you need to multiply the 0.23 into 500. So the answer is 120 mg per liter. So which is equivalent to ppm, 120 ppm. So the next question asks us to find the total organic carbon, that is TOC. Okay, so you know, like, two carbons are present in this ethanol. Okay, so we are again doing the conversion. So two carbons are there. The atomic weight is 12, and the molecular weight of ethanol is 46. So TOC per gram of ethanol. If we divide the 24 with 46, it is 0.52 gram. So 0.52 gram of carbon is there in 1 gram ethanol. Okay. So in C2H6O, how much amount of carbon is there only we are calculating. So only it is 2 into 12 divided by 46 and the answer is 0.52 gram. Again, this much gram of carbon is there for only per gram of ethanol. For 500 mg per liter of ethanol, we need to multiply the answer obtained with 500. So the answer is 260 mg per liter or 260 ppm. This is the amount of organic carbon. Now we have found that 3 moles of oxygen is required to completely degrade the 1 mole of ethanol. So the theoretical oxygen demand is calculated based on the stoichiometric equation. Again, we have found the ultimate BOD to the theoretical oxygen demand and assume the COD is also same. And the BOD at any time t. Here at the fifth day is calculated using the ultimate BOD obtained and the K given in the question. Okay. Next question is TOC, amount of carbon. So amount of organic carbon present here in the ethanol is calculated. The mass fraction is calculated. And for 500 mg per ethanol, it is finally calculated. Okay. Any doubts in this problem? Do you have any doubt? Okay. We'll continue to the next problem. This is a very simple problem. The question is the average airborne concentration of chloroform was found to be zero point 0.4 microgram per cubic meter at 293 Kelvin and 1 atmosphere pressure. The mean concentration of chloroform in water was estimated to be 42 microgram per liter. A typical adult inhales 20 cubic meter of air and ingests about 2 liters of water per day. Compare the exposure via inhalation with the exposure via ingestion. We need to compare the intake in the different forms and we need to find which is higher. Okay. So here this is talking about the air pollution and the airborne disease because of the chloroform. Okay, the concentration of chloroform is given as 0.4 microgram, right? And then the mean concentration is estimated to be 42 microgram per liter. And inhalation rate of inhalation is 20 meter cube. And the ingestion rate of water is 20 liter per day. Okay, so on the with the given details, we will proceed the question. So the air consumption per day is equal to 20 meter cube and the water consumption per day is 2 liter. Chloroform present in the air, which is equal to 20 into 0.48 microgram. So this is what the given as the concentration in the air. Okay. And the concentration given in water is 42 microgram per liter. So you need to multiply 42 into 2 liter. Okay. So the answer is 8 microgram of chloroform is present in 20 meter cube of air and 84 microgram is present in 2 liter of water. The question asks this, you have to compare the exposure via inhalation with the exposure via ingestion. If you compare this, only 8 microgram is ingested through air, but 84 microgram is consumed by in the form of water. So intake of chloroform per day through water is more than the intake through the air. This is very simple. The concentration in air is given and the concentration in the water is given, right? And the amount of intake of air and the amount of intake of water is given. So you just need to multiply them to find the total concentration present. And we have to compare it. That's all. Next question is the concentration of thorium in monoxide sand is 0.04 microgram per liter. So the concentration of a particular compound is given in the sand and the unit of the concentration is microgram per liter. How much thorium is present in 100 kg of sand? Here the concentration is given as microgram per liter of sand, but they are asking for 100 kg of sand, okay? And they have given the information of bulk density. Bulk density of sand is given as 1050 kg per meter cube. This bulk density is based on the porosity. So if we are going to fill the sand in a beaker, say for example, you can use any container of cylindrical shape. So you are filling it with the sand, okay? It will be tightly filled with sand like this. However, there will be a pores occupying in between the sand particles. Okay, what you have to do is initially you need to weigh the empty beaker. Next, you need to measure the weight of the sand which is filled completely in the beaker. Then you have to subtract and find only the weight of the sand. Not, you have to subtract the weight of the beaker from weight of the sand and beaker. Okay, then we have to divide that weight of the sand with that volume, the capacity of the beaker. Say for example, whether it is 250 ml or 1000 ml beaker. And then you will obtain the bulk density. This is how the bulk density is calculated. Okay, this is to give you the idea of how much kg can occupy how much volume of particular area. Okay, so this information is given. Now for the 100 kg sand, what is the volume you need to calculate? Okay, for that what you have to do is you have to you have to divide this weight with the bulk density. Okay, to find the volume. So you know bulk density is weight by volume. Now you need only the volume. So you have to divide the weight by bulk density. So weight is 100 kg, bulk density is 1650 kg per meter cube. And here a simple unit conversion is happening. We are converting this meter cube into liter. So 1 meter cube is equal to 1000 liter. So finally for 100 kg of sand, the volume of equivalent volume of the 100 kg of sand is 60.61 liter. Okay. So now you can easily calculate the amount of thorium in 100 kg of sand because you know that 0.04 microgram per liter is there. Okay, I think that is a mistake. Different units are there. Okay, 0.4 micro. Say if it is 0.4 microgram per liter, then you have to just multiply it with the particular volume of sand to obtain the microgram of thorium in total 100 kg of sand. Here the concentration of chloroform is directly given, okay, and the unit of water and the unit of air is directly getting cancelled. This is also cubic meter cube. This is also in cubic meter per cubic meter cube. And here this is 2 liter and the concentration is also given in microgram per liter. Okay, so it is we can directly multiply this one. But here the problem is the concentration is given in microgram per liter. But this asks for 100 kg of sand. But the one instruction given is the bulk density of sand. So you can convert the weight of the sand to volume of the sand using this bulk density. Then you can multiply the volume of the sand with the concentration to obtain the amount of the thorium present in that much kg of sand. Okay, simple unit conversion is happening here. Next, this is the last problem for today's class. So the question is 10 gram of table salt, which is NaCl, sodium chloride in pure water, is dissolved to make 1 liter of solution. So we are taking 10 grams of salt and we are dissolving it in 1 liter of solution. Okay. Determine for Na plus. For the sodium ions, we need to determine the mass fraction in terms of percentage and also in terms of ppm. Next, we need to determine the mass concentration for the sodium. Next, we need to determine the molality, and normality, mole fraction in the solution. Okay. Already the solution is given. It's very easy. You will see one by one. So the molecular weight of NaCl is, we need to add molecular weight of sodium is 23, chlorine is 35.5, which is 58.5. And 10 gram of NaCl is used, right? So the 10 grams divided by the molecular weight. We know that moles is equal to weight by molecular weight. So in this 0.17 mole, this is the mole of NaCl, right? We need to find the mole of Na plus alone. So what we are doing means we are multiplying with the molecular weight of Na and we get this much amount of sodium is present in this much moles of NaCl. Okay. Then to find the mass fraction in the salt. How much mass fraction of Na is present in the NaCl? What you have to do is 3.91 divided by 1000 grams of water is there and 10 grams of NaCl is there. So 3.91 divided by 1000 plus 10 is 1010 and into 100. This is 1010 into 100 to find the percentage. So it is 0.39 percentage. So again, to convert it into ppm, this is per 100. We need to find it for 10 power 6, that is parts per million. So we need to multiply it with 10 power 4 to make it convert it to ppm. So which is 3900 ppm. Next is mass concentration. Here mass fraction is obtained. Next, mass concentration, which is 3.9 gram per liter, and again it is converted to mg per liter, and we know 1 mg per liter is equivalent to 1 ppm. So with 3900 ppm. Next, we are calculating the molarity. We know this much moles per liter is present, right? So this much moles per liter is present means that much molarity is there. 0.17 moles per liter is there. So 0.17 molarity. Okay, here it is NaCl. So equivalence factor is 1. So if the equivalence factor is 1 means molarity and normality are same. So normality is also same as the molarity. So the normality is 0.17 N. Okay. Next we are going to find the mole fraction. So to find the mole fraction, it is the moles of sodium divided by moles of sodium plus moles of moles of sodium chloride divided by moles of sodium chloride plus moles of water. Moles of water is calculated by weight by molecular weight. Since 10 gram of NaCl is added, uh, the weight of the water is considered as 990. Okay. So weight divided by molecular weight of water is 18. So if you solve this one, you will obtain the mole fraction of the sodium, which is 3.08 into 10 power minus 3. Okay. This is how the mass fraction, mass concentration, molarity, normality, and mole fraction are all calculated. Okay, thank you. We have so I hope it was clear. You have no doubts in the tutorial problem. So for the today's class, we have discussed the assignment 1 and 2 solution. And we have seen the overview of lecture 11, 12, 13, 14. And then we have discussed some sample question for week 3, that is assignment 3. And then we have solved some tutorial problems for this week 3 content. Okay. See you all in the next class. So next Saturday from 3 to 5, I will be handling the next session. Thank you.